which is optimization. So, optimization is the mathematics of finding the quote-unquote best possible way to achieve a certain goal. Kind of like the maximum this that we can have, or the minimum this, like the maximum area, the maximum volume, the minimum cost, the minimum like time used, anything like that. We're just kind of trying to like optimize something. We're just trying to find like the best possible result. So how do we solve these problems? Firstly, we need to specify a function that we need to optimize. What this often occurs in is if we're given like a worded question without a function, we kind of need to like create that function from the words that we've been given. We need to like generate our own function. And that kind of is like where the trickiest part of optimization comes in. And I'll give you guys some tips on like things you can do to help create those functions. The second part is to use the same concepts as in curve sketching, just with the function instead. So what we're going to need to do is kind of use our derivatives to find stationary points and points of inflection and stuff like that to solve these kinds of problems. So we are going to go over some examples of when you might be asked to optimize something, and then we're going to go over some actual examples of applying this. So yeah, some example questions might be like maximizing profit, what I said before, maximizing volume of a box built from a sheet of cardboard. That's a pretty typical one. And then, as I said before, many optimization questions will kind of ask you to rearrange or create an equation. So drawing a diagram is very, very useful. If there's anything about optimization, and I do think we have a slide later on providing some tips for these, but if there's anything that you take away from optimization, and like creating an equation if you're not given one, is firstly draw a diagram. Really, really important, draw a diagram. Even if you kind of think that you're a little bit above it, it's really important just to avoid making mistakes. And if you're kind of new to optimization, it's really, really helpful to look at a diagram and be able to kind of visualize how you might actually incorporate those elements. Otherwise, it's like way trickier. The other thing I'd recommend you take away is just you really need to like practice. Like you really, really need to practice, because they often will give you really difficult optimization questions. Optimization is kind of one of those areas where it's really easy to create difficult questions just out of this first element of like creating equation, because you have to use so many of your problem solving skills instead of just kind of like following a procedure. So yeah, practice, really practice. And then when you're practicing, make sure you're practicing like a range of questions of different difficulties. Start with the easier questions, but then make sure you practice like harder questions. And then when you are practicing these questions, if you find that there's kind of like a strategy that really helps you, or like kind of a few interesting things that you saw on how to generate these equations, write them down, and then you can go back to them when you're studying for your internal and external, because that is just so useful to like kind of have a look back through of your, your big 50% exams and kind of think, oh, a strategy for optimization is to use like Pythagoras or something like that. But we'll go through a few more of those tips once we've gone over these examples. So here we have kind of a very basic optimization question. It's not worded, it's purely in maths, but it's still a little bit more difficult because we do need to create our equation ourselves. Now, a typical thing that you're going to see in optimization questions is you will be able to kind of express things in terms of like two equations, but both of those equations will have unknowns in them. So in our two equations that we've been given here, x and y are occurring in both of these equations. So we can't just use both of these straight up, right? Because we want to find something between p and x, but we don't want this y here. We only want a function in terms of p and x. So what you're going to often have to do is use some substitution. So, summary, optimization questions, you'll usually have like two equations or two like kind of equations that you've been able to come up with, expressed in terms of like two different variables and one thing that you want to optimize, but you want to create a relationship between the thing you want to optimize, and here it's p, and then like one of the variables. So you'll need to use substitution. So in here we know that y is going to be equal to 8 minus x. So we can sub this into here, which is going to give us p equals x squared plus 8 take x squared. Now we can simplify this a little bit. So we're going to get x squared. We're just going to use our binomial expansion. So we're going to have 8 squared. Take 2 times 8 times x plus negative x squared. And it's getting messy, but this is going to give us 2x squared plus 64 take 16x. Now we need to find dp dx. So this is the perfect equation that we have now because we can derive p with respect to x. So dp dx is going to be equal to 4x take 16. And now we need to find the value of x for which p obtains its minimum value. So remember, when we're finding a minimum or maximum value, that's going to occur at the stationary point. So we need to find when this derivative is equal to 0. So we're going to let this equal 0. So we're going to get 16 equals 4x. X is equal to 4. Now, the question asked us to find when p obtains its minimum value. So we need to actually prove that this value is a minimum. And this is one more thing that you should be very, very, very wary of in optimization questions. So often you'll be asked to find like a minimum or maximum value. You need to determine, or you need to like verify that the point that you've achieved is a maximum or a minimum using the skills that we've learned previously in the lecture. Because otherwise you will lose marks, which seems brutal, because, we've only been, we know that there's only one stationary point on this curve, but it's asked to find the minimum value, so we do need to prove this is a minimum. You can do this in a few different ways. If you have a quadratic, you can just say, well, like we do here, a quadratic only has one stationary point, therefore this has to be a minimum. But the kind of typical way to do this, because you're most likely not going to get something as simple as a quadratic, is to use a second derivative test or to use the table of values, like we were doing before when we were determining the nature of a stationary point. So, our second derivative test is what I'm going to do. So our p double dash is going to be equal to 4. So this tells us that the concavity of the whole curve is constant and that it is always concave up, which tells us that our stationary point has to be a local minimum, which is exactly what we needed to prove. That's all we needed to write to prove that it's a minimum. Okay, now we need to calculate the minimum value of p. So all we need to do here is sub in our x value for p. So we're going to have p equals 2 times 4 squared plus 64, take 16 times 4. If you can do that in your head, I'm very happy for you. You probably could, actually, I'll show you guys how to do it in your head, just because practicing the tech-free really is an important tip, which I'll get to in the end. But what we can recognize here is that we have 2 times 16, and then 64, and then negative 16 times 4. So this is actually going to cancel out because 2 times 16 and negative 16 times 4 are actually like terms to an extent, because we have like 2 times 16 and then 16 times 4, which is the same as 16 times 2 times 2, right? Because 4 is just 2 times 2. And as you can see, like, these parts are like terms. So this leaves us with 64 minus 16 times 2. So 16 times 2 is 32. So 64 take 32 should be 32. Yeah. So that was just kind of like a simple way of manipulating the algebra to get an answer tech-free, instead of just kind of like having to do a big, long, arduous list of addition and subtraction. Okay. Perfect. So now we have one more example on optimization. This one is kind of a typical trickier question. Now, as you guys might notice, we are kind of running a little bit low on time, but I do just want to go over this one because it is so important. I want to make sure that you guys understand all the topics that we've gone through in a lot of depth, and then hopefully if we get time, we'll get to our other two topics. So here we have a 400-meter running track, which is made using two sides of a rectangle and two semicircles. And as you can see here, X is kind of like the width, not including the semicircles, and then the Y is the distance between the two parallel lines. Okay, firstly we need to show that X equals a half outside of 400 take pi Y. Now, again, this is kind of a question that we were going over before when I was saying, like, if a question asks you to like show something and then use that information in subsequent parts of the question, if you can't figure out the first part of the question, don't worry, just move on with this equation here, move on with this piece of information and get to the other ones. But we're obviously going to go through how to find this now. So the other thing that I recognize is that we have a pi in here, which probably tells us that we're going to be using something to do with the circles here. So we need a relationship between X and Y. The information that we have is that it is a 400-meter running track, so the perimeter is 400. And then we want to determine the relationship between X and Y. So just kind of at the face of it, what it looks like to me is that this Y value here is actually the diameter of this semicircle, which could be useful in coming up with our answer, right? So what we can do here is we can express this in terms of the perimeter. So we are going to have 400 equal to, and we're going to have 2x because we have these 2x values here making up our perimeter. And now we're also going to have to include the circumference of these two semicircles here. So remember the circumference of a circle, given in your QCE formula sheet as well, but the circumference of a circle is 2 pi r. So we can just write this as 2 pi r, obviously, because like even though we have two semicircles, it's technically just like the circumference of one big circle because there's two of them. And now what you might notice is that we can express this r in terms of y, because y is equal to the diameter, which is equal to 2r, meaning that y on 2 is going to be equal to the radius. So we are going to have 400 equals 2x plus 2 pi times y on 2. So these two 2's are going to cancel out. And now, as you can see, we now have a relationship between x and y. We have a pi in there. This is kind of exactly what we want. We just need to rearrange it to get it into the form that they wanted us to. So they have x isolated, which means that we need to isolate x too. So I'm going to take x over to the other side, which is going to leave us with 2x equals 400. Take pi y. And then we're going to divide by 2, which is going to give us exactly the form that we have been asked to find. So this is kind of a perfect example of like where we needed to come up with an equation ourselves. And it was a little bit more difficult than our previous question because we needed to like consider the diagram and draw everything up and kind of use some more critical thinking skills. So this first part of the question where you need to come up with your own formula is kind of the trickiest part of optimization, and this is the part that I recommend you practice, because when you get to a complex unfamiliar question on optimization, they're not going to give you all of this structuring, all of these subsections of the question, because it's complex unfamiliar. They can give you these structuring questions in simple familiar, but not in the complex questions. So when you get to here, they're not going to give you anywhere near as much guidance in a complex unfamiliar question. So practice, practice, practice. Okay, so for the next part of the question, we need to show that the area inside the track will be used for other events and that its area is equal to 1/4 800y, take pi y squared. So this is a similar thing that we need to do here. So we need to find the area. So our area is going to be equal to the area of this rectangle multiplied by the area of these two semicircles. So we're going to have the area of a rectangle plus the area of a circle. So the area of our rectangle is going to be equal to xy, right? Then the area of these two circles is going to be equal to pi r squared, which is going to be pi y on 2 squared, because our radius is y on 2, remember from the last part of the question. So that means that our area, I'm just going to write this on the next slide, is going to be equal to xy plus pi on 2, pi y on 2 squared. So we're going to have our area equals xy plus pi outside of y over 2 squared. And now the format that it wants us to get us in is we have 1/4 out the front, and then we have kind of a y squared in here. The other thing that you might notice is that our y is in terms of x. So we don't actually have any x values in our area. Take a second, pause the recording to have a think about what we could do here. I'm going to go over the solution now. So what we need to actually do is we need to substitute a value in for y, right? So if you might notice from the last section, we have this lovely little formula, lovely little equation, sorry, of x in terms of y. So this is actually what we need to substitute in for x over here. So for x, we are going to have a half outside of 400 take pi y, and then we're going to have y here again, plus pi outside of y squared over 4. So this is everything we've got now. Now we just need to prove that our area is going to be equal to this form of the equation here. So we just need to rearrange it. So we need to factorize out a quarter, and then we need to like simplify everything that we've got in here. So we're going to have a half of 400 is going to give us 200. We're going to take this y, and then we're going to have a half of pi y. Again, take that y out, so we're going to have a squared there, and have pi. So as you can see, these two here are like terms, or are rather almost like terms. So we can have 200y, and then if we have a half of pi y squared plus a quarter, we have negative a half plus a quarter, we are going to get a negative quarter. So kind of what we have here is we have like a half, negative a half outside of pi y squared plus a quarter of pi y squared. So the pi y squared are like the like terms, and then we can just kind of like do our algebra to combine them together. That's what I'm talking about there. So if we have negative a half plus a quarter, we are going to have negative quarter pi y squared. And now as per the question, we need to take out a quarter. So obviously, if we're taking a quarter out of 200, what multiplies by a quarter to get 200? 800. And then we're just taking the quarter out here, so we're just going to have negative pi y squared, which is exactly what we wanted to prove. Okay, so now that we have that, what we need to do is get onto the next part of the question, which is to find the maximum area that may be enclosed. So what we're going to need to do, remember, a maximum value occurs at the stationary point. So we're going to need to find the derivative when the derivative is equal to 0, and then we need to confirm that that value is actually equal to the maximum value and it's not a minimum stationary point. So let's get into it. Firstly, let's find the derivative. I'm going to do this in this nice green color, a dash. So we're going to have a quarter out the front. Then we're going to have 800 take 2 pi y. So this is going to be our derivative. We now need to find when this is going to be equal to 0. So as you might notice here, the quarter is going to cancel out. We can just take this 2 pi y over to the other side. We're going to get that y is equal to 400 over pi. Now this tells us the y value. We now also need to determine the corresponding x value because we need to find actually, no, my mistake. We actually don't need to find, or the question hasn't asked us to find the dimensions of the running track. Typically, a question will ask you to find the dimensions, but remember, if you aren't asked to, don't do it because you're just trying to conserve time in an exam setting. Of course, if you're just practicing, it might be useful, but in exam setting, don't do anything you're not asked to. What we actually need to find is the maximum area. So we have an equation for area in terms of y, so we can just sub this in. So we're going to get area equals 1/4 800 times 400 on pi. Take pi outside of 400. Oh, what just happened? Side of 400 on pi squared. So now we need to simplify this. So of course, these two pi's are going to cancel out. So we're going to be left with 1/4 outside of 800 times 400 on pi. And then we're going to have negative 400 squared over pi, because we're going to have pi squared down the bottom here, but then that's going to cancel with the one on top. I'm going to take this over to the next slide. So we're going to have equal to 1/4 side of 800 times 400 on pi. Take 400 squared on pi. We can cancel out these 400s because we have this quarter. So we're going to be left with 800 times 100 on pi. Take 400, and we had 400 squared, so we're going to have 400 times 100 on pi. So these are again like terms because we have the like the 800 out the front of 100 times pi and the 400. Similar thing that we were doing before. Again, this is just like a simpler way to do these tech free instead of just kind of like simplifying it all out and then doing like a big long list of addition and subtraction. If you kind of think about it a little bit smarter, then it's usually very helpful. But we'll have 800 take 400, so we're going to be left with 400 times 100 on pi, which gives us 40,000 on pi units squared. And this is our maximum area. The one more thing that we need to do before we move on is prove that this is actually a maximum. So what we can do here is we can use the second derivative. So our second derivative is going to be, I'll just write it over here. Our second derivative is going to be negative 1/2 pi. And this is just from deriving our first derivative, of course. And because this is negative, it means that this curve is concave down constantly, which means that our point is a local maximum. So